Okay, let's talk about DragGAN, which is it's a pretty cool picture editing, I guess, software that that was recently like created an algorithm to kind of um manipulate an image using a GAN. Like as you can see the images up here, you have the line where you can put a few points and it'll open its mouth in the image, or like a cat where you can close its eyes, make change. It's just changing an image in general and kind of moving like parts of the image in a particular way. Here's a video showing kind of like a demo of this where they add some points and like notice how the red points move towards the blue point, and that's how you move the image. And it does a pretty good job of like keeping the features in the image very static, or it kind of keeps the main idea of the picture there. Like this is still a horse or still a cat, but it just moves the part of the picture that you want to move, which is really cool, and it's super easy to do. Um, this is sped up, but I think it does it within like 3 seconds max or something like that to move it, depending on the distance you're moving the points. But anyways, it was a cool demo. Let's see how this works. So this is what it's called. The paper, drag your GAN point-based manipulation in or on the generative image manifold. Yeah, so we're going to be using, or it's going to be using GANs specifically. It uses style GAN 2 right here. Style GAN 2 takes, it was an improvement on style GAN, obviously, and it did a really good job. I forget when it was made, maybe 20. I forget. It was a few years ago when StyleGAN 2 was created. It did a really good job. It was before the diffusion breakthroughs, but the way StyleGAN 2 works is you take noise from a normal distribution. You'll pass this through some or I guess StyleGAN in general. You pass this through some fully connected layers, which kind of disentangles the noise into some sort of latent. And then you take this small little image, or this small embedding, or I guess you could start as a really large embedding. I think particularly they start it as a small embedding, and then they pass it through some convolutions. I'll draw the convolutions in blue. Pass it through some convolutions, but while you're passing it through the convolutions, you also add W there. And W, in a sense, is like a style vector. You can think of W as kind of defining the style of the image, and that's where why the name StyleGAN. That's where the name StyleGAN came from. And then you do this multiple times. And the image grows because you do the inverted convolutions. Maybe one more time. And with enough stacks, you can get like a good image of whatever you're trying to get. This was the basic idea of StyleGAN. You take some noise, Z, from a normal distribution, as you always do, and then you disentangle it using fully connected layers into a style vector. And you take this static embedding, this static starting embedding, and you use inverted convolutions to kind of blow up the embedding size. But as you're blowing up the embedding size with inverted convolutions, the style vector W is added in between those convolutions to give the image some sort of style. Because since a convolution is deterministic, if you just took this, the original embedding, and you blew it up, it would give you the same image every time. But since we're injecting noise into some way, it will it'll change the image in some way. And I guess with W you can do some sort of text like conditioning or whatever. But what matters is you use W as a style vector. And there's actually like two ways to do this. You can use a static W, where it's the same on each level, or you can change W. Maybe you put like a little fully connected layer right here, and that'll change W so that it's a different. Maybe the style needs to be changed slightly for each layer, but that's basically that's the basic idea of style GAN. You have this style vector W that you're injecting into the model as it's creating this image, and then you have, of course, you have your discriminator over here, which takes in the image, but the discriminator is pretty basic. The important part about style GAN was you have this powerful generator, and they leverage this W in this paper in a very powerful way. Let's go to later where they show they give this example of a line and how you can kind of move the line's head from facing forward to facing like to the side using their method. Their method is really it's pretty cool how they do it. So in the style GAN, you have in the generator, you have multiple layers that will generate your image. So this will be like layer 1, 1, 2, 3, so on. And specifically, I'm going to stop at like, I think maybe it was 8 layers or something like that. 8. And specifically, they pick they look at features past the 6th layer, so maybe right after the 6th layer, and then this is your image right here. And remember, each time it would blow up the image, so it would be like small, and then it would be a little bit larger, then a little bit larger, a little bit larger, and then the image keeps increasing in size until it becomes the final output image. So the image is a little bit, or not image, but the embeddings of the image at layer 6 in the generator are they're a little bit smaller than the output image. The output image might be whatever it's generating, but then the latents here on layer 6 are like a little bit smaller, and they represent the features that are going to be generated later. It's some sort of embedding, so it's in a feature space as opposed to pixel space. This is pixel space, and this is feature space because it's an embedding in the model, which doesn't to us it wouldn't really mean anything, but to the model it means a lot, and it's how it generates the image. And what they do is they take this intermediate embedding. And I'm gonna erase. So from layer 6, they take this intermediate embedding, and using bilinear interpolation. I cannot talk. Yeah, bilinear interpolation. They blow up the embedding to the same size as the image. As you can see in this first part, or this first part right here, you have the image here. And then this is the feature from, say, layer 6 in the model. Notice how they have like a part of the generator here, and then you have this intermediate representation, and then you have another part here. That's how they represent it in the paper. But anyways, we take this intermediate embedding from the generator, and we take the image of, this will be our image of the lion. This smiley face, because I am not gonna try to draw a lion. So you take this intermediate embedding, and you're going to so say we have like a point in the image, which I'm gonna show as red, and then we want to move it. In this case, they move it kind of over here. Over here. Actually, instead of showing a line, I'll just show an eye, because an eye is kind of easy to show motion. So we'll have this eyeball right here. So the red represents the point we want to move. and the blue represents where we want to move it to. Blue is T. That is our target point. And red, they define as P. That's our point we want to move. They call that the handle point. And in the blown up, so this is our pixel. This is pixel space, and this is our embedding space. This is our bilinearly interpolated embedding, and you just take like you kind of assume that the embedding space in the 6th layer, like if you put a point in the original image, it'll kind of be in a similar location in the embedding space, since it's not like the 1st layer. It'll be it won't even be close, probably. It probably won't. If we take a point directly from the pixel space and put it in the embedding space, then it probably wouldn't mean anything there. But in the 6th layer, the embedding's probably pretty similar to the pixel space. It just needs a little bit of changing, and but it still has a good representative quality of the features in the image as opposed to the pixels in the image. And that's why they picked the 6th layer as opposed to the 1st layer, which would be too like abstract, where this pixel or this pixel right here wouldn't necessarily be in that location in the embedding space. But they don't pick like the 12th layer, the 8th layer, some late layer, because those are pixel values, and the pixel values are harder to kind of manipulate. It's a lot easier to manipulate intermediate features than it is to manipulate pixels directly. So that's what they do. They project they just take the coordinates and they copy and paste them from the pixel space to the 6th layer in the embedding space. And the idea is that we want to move this point closer to T. You can see that here on the left, where we take this pixel, they actually don't take one pixel. They actually take they actually look at a radius around the pixel. In this case, the radius would be a circle 3 around the pixel. And then they move that that radius of pixels closer to the target. So they kind of move the nose part of the line closer to the target, which is somewhere off to the side. And the way they do that is using this loss function. And what they're going to do is they're going to edit W in a way where the points in the image, the points in the feature space, which represent some sort of features. So you can kind of think of the features here as representing the nose of the line. You want to move those features over to T. So you kind of want to move the idea of a nose to be closer to this area in the embedding space, as opposed to being in the center of the image. You want to move it off to the right. And in this case, in the eye, you kind of want to move the bottom of the eye to be closer to, I guess, the top of the eye. Actually, I'll make the target. That wouldn't make much sense. I'll make the target the center of the eye, the eyeball, or the pupil. That will make more sense there. So we kind of want to shut the eye in this case, and in case of the line, we want to move the head. And the way they do that is we'll look at the first term for now. And the first term is saying for each point around our selected area. So for each point in Q, for each point around like the red point, we want to it's f of qi minus f of qi plus di. And di is that it's the direction, it's the vector in the direction of the target. That's our target, ti. And QI is our pixel. It's a pixel in our radius. So we say so QI would be this pixel at the bottom, and then f of QI would be the features of that. Would be the feature space version of that. So we say we want to move the features, or we say we have these features QI, and we want to move them towards the direction of the target. And in this case, we want to move it one step further. So instead of saying we want to move it directly towards the target, we say we want to move, like in this case, we would have these pixels here. So since I moved it down, it would be here. So in this case, let's say we have this radius, and I have this pixel here, and the new pixel, and then we have TI. So we have this pixel here in orange, and then our vector is right there. It's kind of moved in the direction of TI, which is our target, for the single pixel. Then the second pixel would be, I guess I'll draw that in a different color. Draw it in purple. So then the second pixel would be there, the features, and this would be our purple part, and this would be our orange part. And we're saying we want to move the orange pixel, or the orange features towards the purple features, kind of like moving the features closer to the target. And you just do the MSE between this. This would be the MSE between these two. So it's saying we want to move the features of this closer to the target, and you do that by one step by moving it slightly closer based off the direction of the target. And whenever you do this one step, the features will now be a little bit closer. So we'll draw the feature space, which in this case would be, let's get the pixel on the target. In this case, it would be like right here, maybe a little bit closer, right there now. And then right here, this would be our target. Because we moved it a little bit closer, this would be our handle. And we do that for all pixels around or all features around the selected point. And then the eye would kind of look like this. Be a little bit like more closed, because since the features were moved, then the bottom of the eye kind of moved up a little bit. Maybe the eye changed a little bit, but that's what matters is we're moving the features. We're moving the specific features that we wanted to move. So, like in the case of the line, closer to where we want to move that part of the image. And notice how we're doing it in feature space as opposed to pixel space, because moving the features is a lot easier, because you move the entire nose as opposed, like the idea of the nose in the feature space as opposed to the pixels of the nose, and it changes the entire, it changes the image along with that, so that the image still makes sense. And we're not going to look at loss term 2 yet. We'll get to that in a sec. But the way you do this is you optimize this in terms of W. So you make the features, you make the feature move closer to the target, and you do so by optimizing W, our latents, which represent the style of the image. So you change the style of the image so that the style of the image moves the features closer to where you want them to be. So it moves the nose of the lion closer to where you want them to be. And that's how they do this. That they're just optimizing W so that the features of the selected point are closer to the point that you want it to be at. So the features of the red point are closer to the blue point. Now, after you move W, it may seem trivial to just find the new point, but remember, we're not directly changing the features, we're changing W. And since we're changing W, there's not really like a direct, like we don't really know where like the image shifted. So like in this case, in the eye, like the bottom of the eye moved up, but we don't know exactly where it is. We have an idea where like it'll probably be close to where it originally was, but we don't know exactly. So instead of, since it's not really defined where W moved that part of the eye, we need to find it. So there's a second step in doing this. After one step of optimizing W, which you do so like using gradient descent like normal, then we need to re-find that part of that feature that we were trying to move. And they do that by they kind of assume that the feature that we were looking for will be within like a radius. So like if we look at where this was moved, so let me kind of like draw the original eye. So the original eye was like right here. It's like that. And then the new eye was like will be like this. Now our point is still in the middle. It'll still be right there. That's the point we want to move it to. And then our first target was here. Or sorry, the target's the blue point. Our first handle was this point right here. And then, oh man, I did not want that to happen. Let me fix this. There we go. All right, sorry. Yeah, so we have so our first part of the image was right. Yeah. Changing colors is annoying. Right, that's better. All right, so back to this. So our first eye was the outermost, and then we have the innermost eye. We have the eyeball, kind of squinted a little bit. I guess we could draw like eyelashes on it. Then it kind of shows that it moves some of the features. But I mean, whatever. But anyways, it moved in this direction. But we don't exactly know where it moved. It's somewhere within the radius here. It's somewhere near the original space. And that's the same in this space over here in the target space. Or sorry, in the feature space. The feature that we were moving will probably be close to the feature that it moved to, or where it is in the image, or where it is in the feature space. So the idea is that we look around the original pixel, or we look around the original chosen location, and for the new location. And the idea is that the features that we saw in the original location will be close to the features that let me draw this in orange to kind of show what I'm talking about. So there we go. It moved over there. Drawing it in red was a little confusing. Right there. There we go. So orange is our new point that we moved, and then red was the original point. So red was our original point. Orange is the point moved after one iteration. And the idea is that the features of the image that we were trying to move will be close to the original location of those features before we moved it. So the original location is the red, the new location is the orange, and we basically just search around here for the so we do an argmin. What features are the closest? So we look at the MSE specifically. The MSE is here. So we find the handle point. We see what features are closest, like closest feature-wise to the original features. And if we find features that are close to the original, then the assumption is that we found the closest features within a radius, or the features that are similar to the features we were trying to move in a certain radius will be the features that we were trying to move in the image. So say these features right here represented a nose, and then we move that, the nose in the line. Then we're basically looking for that nose in the feature space that we were trying to move, and we do so by looking in the radius of the original handle point. And once we find that, then we now have the handle point, the updated handle point. So let me go back up here. So we have the original point, and then we move it. So we move. So notice how we move we're moving in this direction, and then the handle point is kind of like right here now. After one iteration, but we don't know where it is. It's somewhere in the radius around the original features or original handle point. And we look around there and we're like, okay, it's right here because the features are the closest to the original features that we were looking at, and they're within the radius we were looking at. So that's kind of how you find it. So there's two steps. First step is move the handle point in feature space and optimize by optimizing W, and then find the updated handle point after you move it. And you do this multiple times. I think they do this like 30 to 200 times. And you do this multiple times, so it slowly moves closer to the target. And then that's how they are able to move parts of the image that you select. Now, there's a second part of the loss component right here, and the second part of the loss component is important for. Let's go back up to the top here. Notice how they kind of have this like this highlighted part, and notice how outside the highlighted part it doesn't move at all. It's only inside the highlighted part where the image changes. So like you can kind of see the lines for moves along with the image because it needs to move so that the mouth opens, but like the paw does not need to move at all because you're not moving the paw, you're just moving the face. Same thing here. Like in this scene, you want to move this part of the scene up, and it moves it up, but it doesn't. And it may change parts of the image inside here, but it doesn't change outside, or at least it tries to minimize that. Notice how it kind of changed a little bit here, but not very much. The rest of the scene is pretty much maintained. Yeah. So the way they do this is by adding another term to the optimization, which is this this lambda. Oh, it's still orange. Which is this lambda times the MSE of f minus f0 times 1 minus m. And what this is saying is this first term, so f0 is the original features. So that would be like this is moved one. This is one step. This would be f0. And then f would be our new features. These are the features we currently have. So this can be after 100 steps, after 1,000 steps, or after one step, whatever features we currently have. And the idea is that we want to take the difference between these features, or we're basically taking, we take the difference between these features and then we mask it. So we're only looking at the features we don't want to change. The 1 minus m, so a 1 would represent I want to mask this spot. So in case of this line, this would be a 1 right here, and it would be zeros on the pixels in here. And you're saying for the features for the parts of the image we don't want to change, I want to take that MSE, and since this is part of the optimization, I want to minimize the distance between the original features and the current features I have. So this is saying I take the MSE of the current features I have and the original features for the parts that were outside the mask. And I do not want to change those features I want those features to be as close to the original features as possible, and that's part of the loss. Of course, you don't have to have a mask, but that's just if you only want to change a certain part of the image. So the part of the images you don't want to change will be as close to the original image as possible. And they use 20 for the weighing term. And that's why you can see that, like, and since it's part of the optimization, it's not a hard constraint where it must follow this. It's just part of the loss so that it mostly follows this. And the higher you weigh the term, the more it follows this. It follows that term. But notice how it has the part of the tree here that changed that wasn't in the original image. But most the scene is basically maintained outside that part. And same with this part of same with the line. So you have the first term, which is moving the points, and then the second term, which is keeping the scene static outside your mask. So that's basically it. You got the two parts, one which moves the point, and one which finds the point, and then you can do some masking as well. Finally, I wanna look at like, this is useful, sure, if I have a good GAN, but like, we have diffusion models currently. Diffusion models are a lot better than GANs at the moment. But say I have an image that I generated in general. It doesn't even have to be a generated image. In this case, they have an image of a person, which is a real image, and you can use GAN inversion to basically find embeddings or like latents in a GAN that represent the image that you want. So remember, we have our GAN has latents W, which represent the style of the image, which is W is deterministic. If you know W, then you know the output image. So you can basically take an image here, which would be the picture of the guy over here, and then you want to find our latents W, which represent the guy. And if we find those latents and we can find we can find a way for the GAN to generate this guy. If we find latents that generate the picture of this guy in the GAN, then we can edit him within this GAN using what was just shown before, the GAN, or the DragGAN part. And notice how it did like a perfect job. Like I can't see the difference between how the GAN represents this guy and the original picture of this guy. Like, it's very similar. And notice how you can kind of move the face around now that it's represented within this GAN. And you can do so with like the hair and stuff. So the idea is that you can take an image from the diffusion model, or like a generated image, and if you get a GAN of something that, like, for example, say I have a diffusion model that generates scenes, I would want to find a GAN that generates scenes as well. I do GAN inversion to find the latents W that represent the image, so that I can generate the image using the GAN, or at least a close enough image using the GAN, and then I can edit it using DragGAN, this paper, then I can edit the latents using DragGAN and generate a new image that is slightly edited, which is really cool. And it's also a really easy way of changing the image. There were, like, for example, they brought up maybe I could use text to change the image, but text is kind of ambiguous sometimes. In this case, it's like a text. You may describe a scene, and you may be like, I want to open the lion's mouth, but it's kind of ambiguous how to do that. It's difficult to tell to kind of prompt it to do that, but it's a lot easier to put points there and say, I directly want you to move this part of the image, the feature, like this feature, the bottom part of the mouth down here, and the nose up here. So it's a lot easier to directly edit the feature space as opposed to changing W based off of text, which is really cool. This paper It's really cool to see, and I can't wait to start using it. I think it's in June where they will release the code to use this, so can't wait for that. Anyways, that is the paper. It's really cool overall. I'm glad to see that we're starting to get to like being able to edit images really easily and really well. Anyways, thank you.